Welcome to Haltech Training Part 19. In this video, we're going to be taking a look at the transient throttle, idle control, and trigger filters on our Pro plug-in boxes. We're going to have a lot to learn, so let's get started. Okay, so let's jump into this video and talk about the transient throttle, idle control, and then our trigger filters we're going to be finding in our Pro plug-in boxes. So we're going to be looking again at the Honda AP1 S2000 Pro plug-in box, and we're going to be taking a look at the difference between the sport boxes and then the Pro plug-in lineup, looking at specifically the transient throttle, idle control, and then the trigger filters. There are going to be a lot of differences between the two calibration types that are going to be specific to the boxes they're going to be using them on. So we're going to be taking a look at that in this video so you understand what to do and what to change and how they're going to be differing. So without further wait, let's jump in and check them out. Okay, so let's get started here. We're going to be opening up our AP1 plug and play file here. We're going to go into the Pro AP1 113 default. And this video we're going to be taking a look at our transient throttle, idle control, and then some trigger settings. They're going to be a little bit unique to this Pro plugin box. Now, if we jump down here in our ECU Navigator, if we jump down into the transient throttle section, some of this is going to look familiar from the Sport and Sprint boxes, but then some of it is going to be slightly different. We're going to be taking a look at that. So let's jump up here to Excel Tuning, to our Excel Tuning tab, and let's first go into our Enrich table. Now, this is going to be very similar in the way this table has been implemented, just like we found in the Sport 1000, 2000 boxes, where we have our transient load source up on top here, we have our engine RPM, and we find that the table has values of milliseconds. And it's going to be an adder when the Excel enrichment is kicked in. So we're going to be setting the highest breakpoint in the table to the highest load source that we're going to find. Now, I can tell you that Haltech's done a really good job with these Pro plugin boxes, and chances are you're not going to have to repopulate any of these breakpoints here because they have found what is going to be the ideal or sufficient breakpoint range for this plug and play box. And I can attest to that fact because I've tuned many Pro plugin boxes in specifically for this AP1, and I really have not had to redefine my load source breakpoint. So that's going to be one less thing you have to kind of look at or deal with. But we have to understand that this load source is going to be coming, if we look down the list here, it's going to be the TT load percentage. That's going to be what this represents. So if you see this TT load percentage here in your channels, if you're live logging, you're going to notice that's going to correspond to the breakpoints here. Now, we're going to see that we have more millisecond here or more fuel to be added at the low RPM. And as we move up in engine RPM, that starts to dwindle out, it starts to taper down. And then the same effect goes as we get up to higher throttle load sources, we're going to decrease the millisecond multiplier here, or the adder, I should say. And that's because we're going to need less fuel as we get up into the higher load sources. So the table is going to always look something like this. Now, if we want to have more fuel at a lower throttle load source, we'd simply just go into the table and bump the values up. And again, they're going to be milliseconds. So it's not going to be percentage, it's going to be based on injector milliseconds. So depending on the size injectors that you have installed, this table may have relevant values or may have values that need to be really reduced. So for example, if we're on a stock size injector, this might be sufficient. If we find that we're on a really large injector, like a 2000 cc, we might have to go ahead and bump these values down because for the same millisecond in the table, we're going to have a lot more fuel delivery on a lot larger injector. That's just something to keep in mind. It doesn't automatically rescale it when we set our injector flow rate in here. We're going to jump down here into our percentage async, and this is going to be that same principle that we found in the Sport and Sprint boxes where we have the asynchronous injector pulses are going to happen after we've delivered the normal injector pulses synchronously in an engine cycle. So these are going to be the additional async pulses that we're going to deliver. And at lower engine RPMs, we have a lot more of a cycle time, so we can add a lot more or have the async pulses be able to kick in. And then as we get up into engine RPM, our cycle time reduces, and we're not going to have the additional extra time to have these additional asynchronous pulses going on for our fueling. So we're going to find that the table is going to look something like this. Now, you can see that Haltech specifically stuck a breakpoint here at 2005 RPM because typically between 1000 and 2000 is going to where you have to have this async increase for this particular plug and play box. Now, one thing to keep in mind is if you're noticing that you have an off idle stumble, so as you start to give it throttle, just free revving off idle, and you notice that it might look a little lean, we're going to attack this async table first. We might bump up the values between 1000 and 2000 here. We might add 10 or 20% to these values. We might be 90 and 70%, and then try it again. Because if we deliver more of the fuel asynchronously, we might find that we actually can richen up the lean tipping condition off idle. So that's going to be one tip that I found. It works fairly well. Next, we're going to find our Excel ignition adjust, and this is going to be how much more ignition timing we're going to be adding from whatever's in our normal base table here. So let's just assume we're riding in the base table here, and we give it throttle. We're going to find that we have additional adders here of 1.5 degrees, 0.7 degrees. We find that at the lower engine RPMs because it's going to help us a little bit more engine response at off idle conditions here. So they've populated the table like this. So next we're going to find our percentage enrichment, and this is going to be a sensitivity table. So it's going to be a multiplier against our enrich table here. So for example, if we jump in here, if we have 100% multiplier value in this table, it's going to be going 100% of the values in this table. It's going to be using all of the millisecond for whatever the RPM and the TT load source percentage we're going to be sourcing in the table is. And if we have something like, let's just say here at 0.5 is at 50%, it's going to be reducing the values in this table as a adder by 50%. So when we jump into this percentage enrichment, if we find that for a situation such as very light throttle changes in transient throttle, we're going to see that we have less of a multiplier because we don't want to have a bunch of fuel being constantly pumped in and added if we're at very small delta load percentage changes. And as we get into higher throttle changes or very high delta load changes here, we're going to see that we have all of the adder from the enriched table. So generally speaking, the shape of the table and having the values that are left in here are going to be sufficient to work with. There's going to be really no real benefit to go into the bottom end of this table and start to increase these values here because you're not going to need a bunch of additional millisecond enrichment if you're having very small changes in your percentage load, your delta load change as you're driving around. So again, this is going to be a pretty well populated table from Haltech already, so we're not going to have to go in and really start to drastically adjust anything in here. Our enrichment decay rate is going to be how quickly we take the fuel out that we've added for the enrichment event when it occurs. And we can see that this table is based on millisecond per engine cycle. So we're going to find that as we go up here in coolant temperature, it's going to add or allow the decay rate to stay in longer because a higher value in here is going to signify that we're going to keep the enrichment in for a longer period of time, and a smaller value is going to be reducing that fuel that's been added here from the transient throttle much quicker. So if we find that if we hit the throttle at whatever coolant temperature we're operating at here, if we hit the throttle and it has a lingering effect, if it seems like it's holding the air fuel a little bit too long after the transient throttle event has occurred, we can go into this table and just simply start to reduce the values. I would usually go in about 0.1 range here of seconds. So a value of a 0.1 will reduce the transient throttle, and then we'll see what it does. We're going to watch the wideband and see if it comes back to an appropriate air fuel after we've triggered a transient throttle event. We're going to see that we have the Excel ignition decay rate, and this is going to have that same concept of decay. This is going to be how many degrees per engine cycle that the spark timing has been reduced if it's kicked in here from the Excel ignition adjust. I, again, usually don't find a whole lot of a reason to use this Excel ignition adjust, and looking here at this decay rate, we can leave this value alone because it's not going to matter if we have 1 or 2 degrees more ignition timing. It's going to hang in for another couple split seconds, so you can leave the values that Haltech has populated in this table here. The coolant temp correction is going to be a multiplier value on top of my enrichment value here. So after it goes through the percentage adjustment here, this percentage enrichment, I'm sorry, for the delta load percentage. So after it figures out whatever it is, it has to multiply, and then it multiplies it against the values in this table. That's going to go through one more multiplication and go against coolant temperature here. So a value here of 0 is going to essentially just be whatever these values in the table would be if we met this percentage enrich, to keep this simple, at 100% here. So say we were at 20% delta load on this breakpoint table, we'd be multiplying the values here by 100% because our coolant enrich at warmer temperatures here is 0. But if we're really cold coolant temperatures, we're going to see that it would be a 400% multiplier against whatever the values are in this table. And that's going to be because we have that wall wetting effect going on. We have to pump a ton of fuel into the engine so that we don't have an engine that's really unsmooth and then it runs lean and runs really choppy when it's cold. That's what the purpose of this table is going to be. So we always want to make sure that at the normal operating temperatures, typically at 176 and hotter here, we're going to leave this at 0. If you have a colder thermostat installed into the engine, or you don't have a thermostat at all, you might find that your coolant temp runs maybe about 140, and in that case, we go ahead and zero this out, because even though that our coolant temperature is only 140, our engine would be warmed up, the engine oil would be hot at that point. So we'd go into this table and we'd make sure at that new redefined coolant temperature of say 140 or 150, we would zero out the value here. We wouldn't leave it at 25% because that's going to be our normal operating temperature with that thermostat out of the cooling system. So let's move into next our idle control. And if we jump up here to our idle tuning tab, we jump into our target RPM. This is going to be the target RPM or desired RPM that we want our engine to idle at. And this is going to be also the start of the closed loop control. It's going to define a target that's going to try to go ahead and apply a bunch of PID control in the background to hit this particular target. Now, just like any other PID-based control in closed loop, we're going to find that we have a base duty. So the base duty percentage is going to define where it should start the PID control from in order to begin the idle control. So let's just make this really simple at the warmer temperatures here. I'm just going to make this a value of 30 just to simplify this table here. So let's just say at a target RPM here of 850 RPM, we require to have at the more normal operating temperatures of 176 and hotter, 30% duty cycle. 30% duty cycle would allow us to achieve 850 RPM. Now, if we did that, we'd theoretically then see that our idle output here and our logger as we're live would be 30%. But we also might find that we define this a bit wrong, and the PID control is going to kick in and it's going to make some adjustments for us. So if we see, looking here at our target idle RPM, if we see it's at 850 and our idle output would be at something like 25%. So we'd see that it's consistently staying at 25% to hit that target idle RPM of 850. We'd have to go back into our base duty table here and redefine this as 25% because the PID control is kicking in the background and making that adjustment for us. So we're going to go and try to populate this table the best we can at the different coolant temperature ranges so that the PID control has the closest duty cycle percentage to target engine RPM that we're requesting here in the table. So we want to make sure that we just check that idle output against our target and then populate whatever our coolant temperature we're operating at. We're going to be populating that particular idle output here because that's going to give us the least amount of work that the PID control has to do, and it's also going to make it a bit more accurate for the PID control. So the next table we're going to find here is our minimum output. Let's just define this as something like 20 to keep these numbers more simplistic. So we're also going to find that this minimum output is going to be the lowest percentage duty cycle that it's going to allow for control. So for example, if we're here at 25% and we limited our minimum output at 20, the PID control, even though it might want to take more than 5% duty cycle out from our table here of 25% to get to the target here, the target RPM, we might notice that our idle output might be something like 20%, and then our target here might be something like 850, but we might see that our engine RPM is something like 950. And that's going to mean that we need to lower this minimum output. We might have to lower it down to something like 10% to allow the PID control to have more of a range of adjustment and allow the duty cycle idle output control here to go down to this lower threshold, this lower capped amount. So it's going to give us more control range. And what that's really going to mean is that if we see that situation occur where it's hitting essentially this minimum output and we're at a particular target engine RPM and we see that our RPM is higher than that, we're going to have to go ahead and lower this down, and then we're going to have to redefine the base duty table because we're going to see that it's going to lower the duty cycle down to whatever it's going to settle out at here in the idle control, the idle output here. We're going to have to go redefine our base duty. But when we first start up our engine and we're doing our tuning, we're going to see that it's based on coolant temperature. So we may have to do a couple iterations of the actual duty cycle versus coolant temperature when it starts up. We're going to be watching the idle output here so we can get a feel for the values against the coolant temperature. We're going to see that it tapers down to a warm temperature here, and same with the idle output. Now, typically speaking, what I find is that whatever the values are in my table here, I'm going to be at least 10 to 15% lower across this table. So you could simply copy this table here, go into your minimum idle output, paste it, reduce your values by, again, 10 to 15%. That'll be a really good starting point. Now, the values that they populate already in this Pro plugin base file from Haltech are going to be sufficient to start and run a stock engine or an engine with basic modifications. But once you start to do large injectors and you start to really have changing the airflow in the engine, if you add a supercharger, you put bigger cams in it, change the displacement, all of this table that they set up here is going to be essentially needing to get gone through and properly tuned. But either way, even if you're on a stock application, I always suggest that you look at whatever your idle output is here and your target RPM, and then you adjust your base duty and go ahead and then adjust your minimum output once you've populated your base duty pretty accurately. But just remember, if you're not seeing it go lower than a certain range of number here, always check your minimum output. That way you can go ahead and reduce that if you need to, so that your idle output can drop to hit that target RPM. Next, we're going to see our post-start offset, and this is going to be how much of a percentage duty cycle it adds when you're going and idling right off of the starting condition. So your starting point where it's cranking, it's going to be at 0 time, and then as soon as it fires up and runs, we're going to have this much of a percentage adder in that cranking mode to fire mode. It's going to be adding to whatever it is. Let's make this a value of 5 to make this easy. So normally, if we zeroed this table out, this post offset here, we'd find that our base duty would be at 25%. We go to start the engine, and it may not start very well because it doesn't have enough airflow under cranking conditions. So this post start will allow us to add some duty cycle percentage to add more air to aid the engine in starting. So we can tweak the values in here to help us start our engine a little bit quicker. And if we find that we have not enough of an engine RPM, so we crank the engine and we find that the engine RPM doesn't really shoot up and go down, so it might only go and crank it. You might only go to 800 RPM and then sort of settle out into your idle RPM of 850. We might have to go and increase the values here, because typically on a stock car, you're going to find that the idle goes up a little bit and then it comes down, so it has that flaring effect. And that's going to be what this post-start offset allows us to do. It's going to taper out after a few seconds of the engine running and go right back to this base duty percentage table. So if you're finding that you have to give it a little bit of gas, give it a little bit of throttle to start it, before you go and make any changes to your cranking, fuel, or anything else, come into your post-start here and start bumping up your percentages, 10, 15, 20% adder to whatever the base duty is here to get your engine to fire off either hot or cold. And we're going to see that at the colder temperatures it has a little bit more offset here. I have found that I do have to mess with this table, especially if I have big injectors and we change a whole lot of stuff on an S2000. You have to go here and add maybe 10 or 20% off the starting condition of this post-start condition so that I can get the engine to fire up very quick and then hold an idle and come down and be stable. Next, we're going to find our AC RPM offset. And this is going to be how much RPM is added to the target RPM here in the table. So looking here at this AC RPM offset, let's just make this whole table value of 50 RPM to make this more simplistic for the numbers. So when I'm going and I turn the AC on, the Haltech's going to know that the air conditioning has been turned on because the button on the dash has been depressed, and then the box gets that signal. And once it gets that signal, it's going to go in here, go into this table. It's going to add 50 RPM at whatever the target is to here. So 850 would then become 900, and we'd see that our target idle RPM here would go from 850 and it would go to 900 because it's adding your AC RPM offset to the target RPM. So that's going to be pretty simple and straightforward. Now we always want to go ahead and idle up our engine, usually 50 to 100 RPMs higher with the air conditioning on than we would if we had no AC on, just because of the load, the drag on the engine. It idles a little bit better when you have it request an idle up or a little bit higher RPM. We're going to see that we have an AC start point offset. And this is going to be how much duty cycle increase is going to add to our base duty table here to hit this AC RPM offset. So we're bumping up the idle request here, 50 RPM, and this is going to correspond to how much more duty cycle has to be added to our base duty. And what we're going to find is if we turn the AC on, we see their idle RPM here, target RPM goes to 900, let's say in this example. Our idle output here goes from a value here of 25%, let's say it was controlling and it was happy there, but all of a sudden now we see that the idle output goes to something like 35% to maintain that target idle RPM of 900 that we're requesting with the AC on, we would have to go ahead and look at what the value was in this table here, and then look at what our base duty value was. And if we see that it was at 35%, we'd know that this 5% adder here wouldn't be enough. We'd have to go ahead and maybe make it 10%, because 10% plus our 25% here would give us the idle output, the corrected value of 35%. And then our PID control would not have to go and kick in and make some adjustments in the background to get us back to that higher AC RPM offset request that we're going to find here. So it's going to be pretty straightforward to set that up. Next, we're going to find we have ignition correction. Now, the ignition correction is going to be an offset, an adder or subtractor based on whatever our target idle RPM is at. So, for example, here, if we have a value here of a target RPM of 850, if we jump into our ignition correction, our 0 point in the table here, or no adder or subtractor for ignition timing, is going to be based here at 850. But if we get to a situation where we're going below that RPM, say we're going down to something like 750, that would be this minus 100 from our 850 target, we're going to find that we're adding 11 degrees ignition timing to whatever is in our zero throttle timing. So this is going to be something that we have to keep in mind. Whatever the values are in our zero throttle, this ignition correction is going to provide an offset, either adding or subtracting, to be able to maintain and stabilize our idle RPM, and it's going to be trying to hit that target. So it's going to be another way that it provides an offset to hit our target RPM. Now the goal here of setting up your idle control is going to have to be working with your zero throttle timing. So if you find that in this base duty table here, if you're really increasing the values a lot to try to get to your target idle RPM, you might go into your zero throttle timing and then bump the values up in here in your spark timing. You might add a value of 5 degrees to the whole zero throttle table here. And what you're going to find is if you bump up the ignition timing at idle in the zero throttle table, it's going to be essentially giving you more torque and then increasing the idle RPM. And what that's going to happen at that point is you're going to have to go into your base duty and reduce your base duty table down. So if you're finding that you're putting really large values here, 50, 60, 70, 80%, go into your zero throttle timing, add timing. That'll help you bring down your base duty percentage here, and it'll stabilize the idle a bit. And that's going to be something else you have to keep in mind with ignition correction. The values that we have in here are going to be ballpark to start with. If you find that your engine is very sensitive and it wants to dip down an engine RPM very quickly, that your idle RPM control here isn't going to add enough duty cycle to catch it, we're going to want to use ignition timing and be a little bit more, maybe more aggressive. If we find that we might add 20 degrees here, and if we just do an L horizontal interpolation, we might go and have more aggressive ignition timing adder if it tries to get into a stalling condition or dip down an engine RPM. So don't be afraid to experiment with this and have more aggressive ignition values in this table to see if it can help further stabilize your idle output here for your target and your actual, to see if they're going to be tracking a little bit better and you're not going to have that dipping effect as you're coming down to your idle from maybe deceleration, or if you're free revving and coming down so it doesn't have as much of a dip. Next, we're going to be finding that we have our P, I, and D terms, and we're going to see that our P, I, and D are in the tables here. Our proportional specifically is going to have this 0 being a value for AC off, 1 being for AC on. Now we can see that we have two different P values here, and that's because with the AC on, the feedback control has to be a little more aggressive, and that's why you see this P term has been increased from 25 to 35. Typically speaking, these PID values, we see that the derivative 0, these PID values here are going to be sufficient to allow this closed loop control to work properly. Now, very rare instances that I want to have maybe more aggressive feedback from my duty cycle percentage here, I might increase the values here in my P term, but typically speaking, again, we can leave these values alone and just concentrate on setting up the tables and setting up our idle control and our zero throttle timing and our ignition correction. That's going to typically be sufficient for 99% of the applications where you don't have to go in and start tweaking the PID values out in the table, because they've already done that for us. Now, the last thing we're going to be looking at here is our trigger. Now, if we look at this table, it's going to be our trigger angle offset. So if we jump up to our setup and main setup here into our main tab, we're going to find that under trigger, we're going to have our trigger angle. And the trigger angle is going to specify where it's going to reference its timing point to do its engine position calculations and our engine speed calculations, and to have us deliver the ignition timing that we're requesting in the table. So it's pretty straightforward to figure out the trigger angle and what that means. But this table here is going to be an offset to our trigger angle found here. So 50 degrees is that point where we found it's going to be sufficient to, or going to be the point where we have to have for our ignition timing to control from. So it understands that that's essentially our 0 point to calculate from. Now the values here are going to be offsets to this value here, because we're going to find as we rev the engine up, it's going to have a drifting effect with our ignition timing. So this table is going to go ahead and have a background compensation so that this trigger angle here is going to essentially be always varying with engine RPM to have our ignition timing be more consistent. If we didn't have this table, when we free rev the engine with a timing light on it, and we had our trigger angle locked here at 50, we'd notice that the timing would slightly vary a few degrees, and this table is going to take care of that for us. So typically speaking, this trigger angle offset can be left alone, and we can just run with what's in that table. I really haven't found a reason to go and change this. Typically speaking, if you put a timing light on, you'll use this lock timing feature. You go in and set your trigger angle, and if you free rev it and you put the light on the crank balancer, you're going to see that the value should be fairly consistent to whatever you've locked to your timing, even at high RPM, something like 7,000 or 8,000, because of this trigger offset. And again, I typically don't have to change this table or modify it, so we're going to be running with the values in that table. We're going to be looking here lastly at the trigger voltage home and trigger voltage threshold level tables. Now these tables are going to provide a background filter for the magnetic sensor pulses coming in from the crank and cam sensor on this S2000 application. They're going to be providing a way that we can ignore or filter out the raw voltage coming in so that we don't pick up and get a bunch of misfire conditions, or if we look here at our home counters or the miss counter, we're not going to count extra teeth or have any kind of oddity going on when we look at our actual cam and crank sensor pattern. So it's essential that we have some kind of a voltage here, or again, we could pick up extra teeth, and the Hall tech may go and not know what to do and have misfiring because it can't calculate the proper ignition timing and where to spray the injectors and on and on and on. So I usually leave these tables alone. Now, if I find that I'm having a difficult time getting the engine to fire off under cranking, if I found that I went into my cranking timing tables here and my pulse prime table and even my cranking ignition timing table, and I've tweaked those values the best I can, and I'm still finding that I might have a little bit of a lag till it starts, or we might notice as we start to crank, the engine RPM here stays maybe a little low for a second or two, and then it starts to pick up as the engine cranks, and our battery voltage is sufficient. I might go in here at 250 RPM thresholds in both these tables and lower my filtration level down to my threshold level. And what that's going to do is allow the cranking, under cranking RPM, allow the cam and crank sensors to have a larger output that's going to be read from the Hall tech that'll aid our starting a little bit faster. We have to be careful that we don't make these too low to the point where when we're doing our cranking, it's going to be, again, counting in this diagnostic, it's going to go ahead and count extra teeth, and it's not going to know what to do, and it won't allow it to start. So we have to be careful. But if we jump into the 250 threshold here, we can lower it down a couple tenths here, and it usually is still okay for cranking. But the values in here will start and run a stock S2000 or even a modified S2000 very, very well. 99% of the time, we don't have to touch these values. And at the top of the table here, we can see, just kind of going through both of these tables, the threshold changes and it starts to go up to 5 volts here. And that's going to be the filtration at higher RPM. If we notice that we're starting to get some kind of a misfire condition going on, and under diagnostics, if we're seeing that this miscounter is counting up and we're having all kinds of problems, and we've gapped the spark plugs and that's still not going away, it's still having this misfire problem, we can't resolve it, then what we can do is go up here to this 4,000 RPM. We might have to increase the voltage threshold in order to make higher RPM pulls and not have any kinds of problems. We might go in and make this 5.5 for both of the home and the trigger thresholds here. Again, typically this is not going to need to be done. Usually if you're having a problem and you're getting your misfire counter counting up and it's throwing all kinds of errors at high RPM, there's going to be something wrong with the camera crank sensors. But every once in a while I see that I can go in here and increase these thresholds, which will clear up any kind of high RPM misfire that I have going on if I can't really
pinpoint it, and I've exhausted all of the troubleshooting on my end to make sure that the cam and crank sensors are in good shape and everything is working properly. So hopefully now you understand how to use this section of the software here between the transient, idle, and the trigger, and you'll be able to apply it to your SC1000 if you do your tuning. And in the next video, we're going to be checking out a whole bunch more features in our file here.
Okay, so that wraps up Haltech Training Part 19. In the next video, we're going to be taking a look at some more features and our Pro plugin boxes. We're going to have a lot to learn, so I'll see you in the next video.